Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 40, we will learn about semi-supervised learning. So even though this particular module is supervised learning part 2, but I have one lecture on semi-supervised learning has been included in this particular module. So the different concepts that we will cover will be on semi-supervised learning, then on semi-supervised learning assumptions, then some major categories of semi-supervised learning models, graph, then within those graph-based semi-supervised learning model, label propagation algorithm, label spreading algorithm, wrapper method, clustering-based semi-supervised learning models, active learning plus semi-supervised learning with human-in-the-loop models, and finally we will look into some examples using our old dataset which we have used earlier regarding our decision to use a bicycle or not depending on weather, forecast and other conditions. So, semi-supervised learning is, from the name itself, it's obviously somewhere lies between supervised and unsupervised learning. So, what happens over here is the models learns jointly from both labeled and unlabeled data sets, right? Unlabeled data within a data set, right? So, that means what happens is sometimes in real life, whenever we are collecting data on certain aspects, we may not collect the data about when we do actual survey, we can only get a small survey done, right? The sample size is not that much. But I may have raw data on many aspects, right? I just don't know the final outcome of the decision. So sometimes what we can do is we can do some amount of surveys and the rest amount we can also, based on the nature of the data, I can also, extend those learnings from that labels into the, the unlabeled ones as well. Or the other way, we also use the properties of unlabeled data, which we have learned earlier, like clustering, different forms, in where we can find some amount of rules of association. We can use those learnings from unlabeled data and mix it with rules that we have learned from labeled data set. That is where we, train a model based on the, labels. So both techniques could be combined together to give predictions for the unlabeled data. So that is what happens in semi-supervised learning. And usually the unlabeled part is, much larger. Why? Because that is, we can only do surveys of very, small data, a few samples. We cannot do very large surveys because then the survey would be very expensive. It would be slow. It would be sometimes subjective. Means we are not also sure that if the data we are collecting is, it may be varying as per different context and situation and so on. So surveys are both limited, usually done for limited samples. Those are costly, and but in many cases, particularly when we are dealing with urban planning data, spatial data, then we have got remote sensing data and certain other kinds of data sets, but we don't have the labels or the outcomes of those particular data. So that is where, when we have extensive data sets and only little bit of surveys done or ground truthing done, then we can go for this kind of approach to find the label for the unlabeled data. So you can see the formulation, which is pretty simple actually. So D is the total data set. It is made up of both DL, which is labeled data, and DU, and it's a union of both DL and DU. Now DL includes two kinds of data. One is the input feature, that is XI, and the labeled data, which is YI. And using this, we can actually predict that, okay, this is the part of the labeled data set, right? And total samples may be L. Now, the other part of the data, which is the unlabeled part, where we have only got Xj, that is only the input features are available, and the number of labels also, we don't know the labels of this particular data, and the total unlabeled samples comes to around, because we already have L number of label samples and total N is the total samples, so N minus L, right? And obviously L is very, very lesser than N. So number of labeled sample is much smaller than the total samples. So labels are as we discussed, levels are difficult to procure, and we have to do actual surveys and all those things. So this is a technique which also could be adopted by by extending the power of both the learnings that we discussed just now, that is both from all the algorithms that we have learned earlier. Somehow or other, those could be combined together to come out with this semi-supervised learning algorithms. So when we are dealing with semi-supervised learning algorithms, then we are doing some basic assumptions. What are those assumptions? The first assumption is the smoothness assumption over here. Now, smoothness assumption basically means if two data points are close to each other in a feature space, they are likely to have similar output levels. So that means if those two data points are close to each other, then most likely they are the same thing. So obviously, it is not a rule, but it's an assumption that we are doing. In generally, that is true. So what it also means is, it means decision boundaries. Whenever we are trying to separate two clusters of data or two groups of data, we have a decision boundary which we use to separate them, and the decision boundary should pass through low density regions and not cut across dense neighborhoods of similar observation. So because we are now considering the distance, that means if things are close together, better not create a boundary between those two, because those two must be similar. Same way, there is the assumption of cluster, that is cluster assumption, where data naturally form distinct groups or clusters, and samples belonging to the same cluster are likely to share the same level. So that means here also, we are learning, this learning comes from the clustering algorithms that we have learned, that is because data naturally forms clusters, and samples belonging to the same clusters are most likely to have the similar levels, right? So classifier in this case should also place decision boundary between clusters and not within the clusters. Then the third assumption is manifold assumption. Now what it says is, usually data exist in a high dimensional feature space. Many features could be there for one particular row of data or one particular sample, but the actual meaningful variation in the data lies on a much lower dimensional structure, or otherwise known as a manifold. So what we do is, suppose in an example there are 20 deep its feature space, like there are 20 features, but we will see that real behavior of the data depends on only 2-3 underlying factors or latent factors, right? Latent factors concept we have discussed earlier, where we have said that, well, some of the factors are totally irrelevant, other factors are also, there is collinearity between those factors. So what we can do is, we can combine those factors, giving a sort of a unitary following a unitary method of adding those up and creating something called a factor score, right? So that means those latent factors actually represent those 2-3 other factors, right? So we can bring down the dimension of the data. And so that approach also could be done over here. And semi-supervised model exploit this intrinsic geometry of the data distribution to improve learning. So what happens when you can reduce the dimension of the data? It is more easier to find meaningful relationships between the different kinds of samples that we have. So that is why bringing down the dimension actually is easier to do some sort of prediction, some sort of finding the relationship between the features and so on. Now semi-supervised classification could be done for where we could be doing both classification as well as regression. Now regression basically means there are continuous levels, the levels values are continuous, and classification basically refers to when the categorical levels, the levels that are there are categorical in nature, right? Either it's a binary categorization, or it could be a multi-class categorization. Now because we are working with unlabeled data, in other cases we will say that the missing levels should be encoded at -1. That means it doesn't have a label at all. Now this semi-supervised learning models can be both linear and non-linear in nature, because because of the nature of the data, it depends on the shape of the decision boundaries and how unlabeled data is utilized with the labeled ones. So primarily this we have learned earlier. That means the decision boundary, the shape of it decides if it's a linear or a non-linear data set, and in that if it's a non-linear, then probably we cannot it means that we cannot divide the data into two parts using a straight line or so. And similarly, along with that, how unlabeled data is utilized with the labeled ones, that approach also determines that if we are going for a linear process or a non-linear process, right? So, linear SSL models sometimes can extend logistic regression or SVM. We have learned both of them. What is done is by incorporating unlabeled data through regularization or something known as self-train. Now, what it does is first we train the linear model, either SVM model, logistic model, whichever linear model you take. We train them on small labeled data set DL. Whichever data sets are labeled, we will train on that, right? Sometimes we also do train to split over there as well. So, usually we train it on the labeled data, and then what we do is the pseudo labels for DU are predicted using the rules that we get from the from the previous labeled data. That means the decision boundaries we get or that equation that we get from for doing a regression using this labeled data, we use that equation or that decision boundary to also do the prediction for all the unlabeled data as well. So after the prediction, we call them to be pseudo labels, right? Now, once it is done, now we have got labels for both pseudo labels as well as original labels for the entire data. Then we retrain the linear regression model again, and because we have because earlier it was only training on DL, now we are training both on DL and DU. So again we do that, and once we do that, again the linear boundary is then adjusted based on the data distribution. So you get a new equation, a new decision boundary, right? And as soon as you do that, you do the prediction again, right? And you retain the original. In some cases, we can retain the original data set. Sometimes we also, allow some amount of change in that as well. And once it keeps on doing this in an iterative manner, and finally, once it stabilizes, the results stabilize, we check that, the model is trained. So usually if you see, there are different examples of this kind of models like semi-supervised SVM, self-training with logistic regression. So I have highlighted self-training because it is first training itself using its own level data, right? And semi-supervised linear regression, co-trainings, these are the different models which come in this particular approach. Then nonlinear SSLs capture complex structures such as clusters, manifolds, non-linear relationships using unlabeled data. So that means here we are more focused on trying to understand which things are clustered together, or which we are also looking at dimensions, right? So all this actually plays a role in determining that, okay, which one would be important. And then there are nonlinear relationships using unlabeled data. So those relationships also could be explored. So more or less, all these are considered when we are, creating a nonlinear SSL model. So the decision boundary fx is equal to nonlinear function, whichever we adopt. It could be kernel, graph, neural network, any one of those, right? So some of the examples of this model are label propagation, label spreading, semi-supervised neural networks, graph convolution networks, kernel-based SSL, and so on. Okay. So actually, clustering and all in this particular series of lectures, it comes after this. So it would have been better if we have done clustering earlier, and then we would have done this. Then it would be much more easier or fast for you to understand, because there are several concepts which we have not done earlier. But in any case, or neural network also we have not done till now, right? So, but still understand that these are the methods when you go back to when you do learn clustering and neural networks and all, you can always revisit this lecture and then you will have a better understanding. So some of this nonlinear SSLs are label propagation, label spreading. These are two very important ones which we have discussed earlier as well. Semi-supervised neural networks, graph convolution networks, kernel-based SSLs. So usually there are several algorithms there, but these two are very popular. And some of the major categories of SSL algorithms, if I don't divide them as per linear, non-linear, and so on, it could be, we can say some are graph-based methods such as label propagation, label spreading. Some are self-training based methods or wrapper methods, we call them, like the one that we discussed over here. Some could be clustering based methods. Some could be deep encoder based SSLs, and some could be active learning plus SSL semi-supervised learning with human in the loop. So we will discuss this gradually. So when we are talking about graph-based semi-supervised learning, the entire data sets, both labeled and unlabeled samples, is represented as a graph structure to capture the intrinsic relationships among the data points. So in this case, observations are not treated independently, right? So the model learns from using the relationship between the observations. So that means we are connecting the observations, right? And the connection actually determines that, okay, which is closer, which connection is stronger, all these things is determined from that. And then determines which, because it is nearer, it is connected, it is most likely having the same level, right? So that's the concept. So usually we take the groups of nearby data points which are near to a particular data point, and because the connected data points, of course, with similarity values and so on, and we can take aggregate score of prediction for those values and can predict the class or that level of this particular data point. So this is represented like this: G equal to V, E, W, where V is set of vertices or nodes where each node represents a data point. It could be either labeled or unlabeled. Then E is a set of edges representing connections between similar data points, right? Then Wij is the weight of the edge between node I and node J, indicating similarity strength. So this is highlighted because this is the key term that we use to determine which should get connected and which should get not. So observe, and what we do is edges are created based on similarity in feature space. So if those are, this similarity, that means based on similarity strength, based on that we actually connect the edges, right? If 2 points are similar, and edge is formed if between them, obviously. That means that's the assumption. That is, because those 2 points are similar, there is a edge, right? Or otherwise, if there is a strong edge, then those 2 points are similar as well. So closer points indicate stronger connections. So we already have done this assumption of smoothness earlier, and so that we are assuming here. So now how do I measure this similarity, right? So it is basically, everything is a distance-based measure over here. That means, as we have discussed at the beginning, that things which are nearby are more similar, right? Or connected, those are more similar. So in this case, we can have different functions. We could have, KNN, or we can have, this RBF, radial basis function, or kernel, right? So this is a kernel function, radial basis RBF, and this could be used as the similarity, function. Now, this kernel function, if you see, it is Wij, this is the weight of that connection, how strong it is, and then xi minus xj square normalized, it's a squared Euclidean distance between the data points, and sigma is the bandwidth parameter which controls the neighborhood size. That means from one point, what is the neighborhood that I'm considering and what are the points within that, right? So that distance is the bandwidth, right? So this becomes very important in other algorithms also, right? So this bandwidth parameter is very, very important. It governs that, okay, how much stress you are giving to near data and so on. So the RBF kernel ensures local smoothness, strong influence of nearby points, and weak influence of distance point. So that is what this actually ensures, right? So that means things which are within the the bandwidth and all has got more influence definitely. And we take a exponential distance decay function over here. So that's why we take a exponential not distance decay function here. So that means it reduces exponential. So coming to the different specific algorithms within the graph method, one is of course the level propagation algorithm. Now over here what we do is levels, we know that only a few nodes are having the levels, and this levels from this small set of level nodes are iteratively spread or propagated to unlabeled nodes based on the similarity structure of the data graph. That means what? I have a point, based on similarity I will say that these points are similar, and then some points may not be similar, right? And from here again I can move forward. I keep on expanding, right? And we will not run out of all the points in all directions. So some are similar, some are not, we are getting, so accordingly we can form the clusters. We can actually we can propagate the level, not form the cluster, sorry. So accordingly we can keep on propagating the level in this particular network. So first we do construct a similarity graph, right? And using RBF as the distance similarity function. So node represents data points and edges represent similarity using the RBF function between the points. So this is what we first do. And then similar points with weighted edges are connected. The edges, similar points are connected, and this connection has got a weight. And gradually levels are diffused across the graph, and that means things which are similar will get the levels of the surrounding, points. And then gradually this graph actually expands, or gradually the levels keep on, diffusing throughout the graph. And the algorithm stop when the levels stabilize, and then there is no change in the levels at all. So what we can say that the new level of each node is the weighted average of the levels of its neighborhood nodes. So that means of levels of neighborhood nodes determine what would be the level of the nodes that is under consideration. So usually that as you see that we keep on updating the data points, right? For example, for every iteration, the previous value changes to the new value, and what is actually changing? What is changing is the levels are getting propagated, right? So in each iteration that is happening. So over here, if you see, this F is the level matrix, and what it contains is basically it's a matrix of, it represents top level distribution of data points. For example, if a data point has got 3 classes, then it is actually Fi is stored as like this, which means class 1 has probability of 0.1, class 2 has probability of 0.8, and class 3 has probability of 0.1, meaning the point most likely belongs to class 2, right? So whichever is the highest probability, we will take that, right? So that means that we have a matrix where for each class I can predict the probability. Then W is the similarity matrix. Now what is W? W is the Wij value that we calculated in the previous slide, which is similarity between node I and j computing using the RBF kernel, or it could be using KNN kernel as well. So either using the KNN measure or using a RBF kernel measure, we can actually measure the Wij, which is the value of the strength of the connection between the two data points. And this WFT aggregates levels from similar neighbors. That is, that is just W, that is this one, and this FT, what it does is it is taking the levels, because F is the level matrix, it is taking the levels of the similar neighbors, and then it is normalizing it again with something like D, which is the degree matrix, and Dij is equal to summation of j to Wij, and it's a diagonal matrix that represents total connection strength of node I and j is used to normalize the influence of neighbors, thus multiplying by d minus 1 normalize the total connectivity. So Dij is summation, actually Dij is summation of all the Wijs, right? So this one, for every kind of similarity, between 2 points, we are measuring the Wij value, right? This point to this point. But it is also normalized by summation of all Wijs, right? All similarity values. So that is what is being done. And this normalization is done because when you normalize, then if there is a bias towards one in a few group of data towards one value, then that actually doesn't creeps into the this particular problem. That problem doesn't gets to that will probably lead to wrong predictions here. So to remove the effect of that bias, we do this normalization. So then there are two constraints. One is labeled nodes remain fixed, and unlabeled nodes update until convergence. So that means labeled nodes doesn't change value. The unlabeled ones, keep on updating their value until there is convergence, right? Because we are propagating in different direction based on similarity. So every time the similarity value is changing and the that Fij value is changing, so it is Ft value is changing. So he keeps on updating the unlabeled data labels, and eventually we reach a point when there is not too much change, and we adopt that as the solution. So the algorithm goes like this. First, we construct the similarity graph either using KNN or RBF. Then we initialize the levels. That means labeled ones are obviously the true levels. The unlabeled ones we initiate with 0. That means there is nothing predicted. Then we compute the weight matrix Wij, which tells how similar point I is to point j, and if the value of Wij is high, which is very similar, we say it's a strong connection, and if Wij is low, then it's not similar or weak connection. And then after I calculate Wij, I also then normalize the graph. So nodes with many neighbors don't dominate, as we were discussing just a little bit ago. That is, some nodes are connected to many neighbors, right? Other nodes are not connected to only a few neighbors. So when you normalize, you average it out, right? So then those effects doesn't, remains that much. And then once we have done that, then we iteratively update the levels, because now that after normalization we can, measure the, we can determine that what would be the level based on that, this part, that is where we were, considering the new level is the weighted average of the neighbors level, right? So that is, we will iteratively updating the levels, and the new level comes in, and then based on that we will keep on, once it is done, then we again run the algorithm, and this keeps on happening till there is very little change or there is convergence. And that means when the difference between ft and ft plus 1 is so less, it is, it's a very extremely small value, then only we will stop. Then comes the level spreading algorithm. Now, level spreading is more stable than level propagation. It performs smoother and regularized level diffusion across the similarity graph, allowing slight adjustment of the labeled nodes. So, in the previous one, we were not changing the label nodes, it was fixed, whereas the unlabeled nodes were changing. But over here, we have a scope to change the label nodes as well. And this makes it more robust to noise and prevents overly rigid or abrupt labels assignments, right? So that means the entire process becomes much more smoother, right? And it goes, the prediction also becomes much easier. So level spreading adds regularization and soft clamping, right? Now, what is this soft clamping? What is this regularization? Basically, what it means is, instead of, in the previous example, we have only, one part. Now here there are two parts to the equation. One is this part, which is same as the previous one, and this is the new part, right? Now this part actually spreads level across the graph based on, different, things. And this 1 minus alpha y pulls level back towards the original known levels, right? So that means this is where we will try to keep it as fixed as possible. So ft is the current level matrix, which stores soft level scores for all data points at iteration t, that is each row equal to level probabilities of a point across the different classes. Then S is the normalized similarity matrix, right? And uses similarity graph, either RBF or KNN, to measure strength of connections between nodes. It is also normalized to balance the influence of neighbors, same as the earlier one. And then y equal to the initial levels or the original levels that we have got. And this alpha, which is either 0 and 1, it's a clamping factor which controls the balance between diffusion and level retention. So if the alpha value is almost equal to 1, that means we are giving more influence from neighbors. That means there is more spreading. And if alpha is almost equal to 0, that means more influence from original level. So that means if alpha equal to 0, that means the original level remains. If it is not, then there is, some influence, and that means there is some changes in the y is being allowed. And so that's why this is a factor which actually either sticks to old, results, or it allows some change. So that's why we call it a clamping factor. So in level propagation, level nodes are fixed, which is hard clamping. But in level spreading, level nodes can slightly adjust during iteration, so it is called soft clamping. And 1 minus alpha y ensures solutions stay close to the original levels while still allowing smooth diffusion of the levels. So then comes the wrapper method. In this is already, we have done a bit of that in the earlier, when I was explaining. So this model gradually increases the size of the labeled data set by adding highly confident predictions from the unlabeled data. right? It is commonly known as self-training. So self-training example we give, we use a existing classifier like logistic or linear to predict the outcome for the labeled data, right? And once it is done, we can use that model to predict for the unlabeled data, and then we keeps on iterating. So this update rule comes like this: the labeled data set at iteration T1, this is the labeled data set DL, it equals the previous labeled data set DL at time T at the T period, and new pseudo-labeled unlabeled samples, right? And new pseudo-labeled unlabeled samples basically means that means this this is a union sign, and that means over here we are also adding the pseudo label samples. That this is the pseudo labels, because X is the features and this Y is the pseudo predicted levels. So we are adding both of them up together to give the final outcome. So so what the steps are: you first train the model, then we do predictions using the trained data, of course the labeled data, and then we start predicting. The ones which are predicted with higher confidence, only those are selected. So select confidence samples, that means the predictions where the confidence level is high, we select them, and then we retrain the model, and we keep going on, right? So gradually we increase the confidence levels of all the different unlabeled samples, right? And sometimes we use and then we we keep on retraining till there is convergence, and we use a loss function to determine the convergence, where L equal to L label plus alpha into L for pseudo, for the pseudo labels, right? So what it does means is model learns by minimizing error on true label data plus a weighted error on pseudo label data, where alpha controls how much the model trusts the pseudo labels. So that means this is again a parameter which we can tune. So you understand over here, that means in the earlier example we were talking that we predict for using the label data, we generate a model or a regression line or a equation or a plane to divide the data. Whatever we do, using that we predict for the entire data, right? Unlabeled data. But here what you see is we are not predicting for the entire unlabeled data. We are definitely predicting, but we are keeping those results which are confident, whether we are within the confidence interval, right? And if it is not, then we are not keeping that data, and we are again retraining the model, and then probably in the next iteration those would get trained, the samples which were left out. Then we have then the next method is clustering based on semi-supervised learning, which is clustering based semi-supervised learning, which is very, the concept is if the point is in the same cluster, then it will share the same label. That means there could be cases where some cluster will contain label points, some cluster contain unlabeled points, some may contain both. So there could be different combinations, but the basic idea is if there are labeled points within the cluster, most likely the cluster will have similar labels, right? Or it may be aggregated to find, or some strategy to find what would be the labels based on the existing labels. And if there are none, then there are also other strategies. So here also we usually use the k-means or the DB-scan clustering algorithm is applied to detect cluster structure, and labels are then assigned unlabeled cluster, and the labels are then assigned to the unlabeled cluster member, right? So that is how it works. So first of all, of course, you will ask me what is k-means and DB-scan, but that will be covered in unsupervised learning, which we will cover in the next module. So again, I'm saying once those lectures are done, you can always come and revisit this. So the majority, now once we do this, then once we have done the clustering and all, then how do I determine the unlabeled points, right? So there are some strategies. One is, of course, majority voting. That means unlabeled points are assigned the label that is most frequent, right? And otherwise it could be centroid based assignment. What it means is label point closest to the cluster centroid is assigned to all unlabeled cluster members. So that means if I have a data points like this, and then I do a clustering, right? So this is cluster 1, this is cluster 2, this is cluster 3, and this is cluster centroid. This is based on all the data points, this is based on all its features, this is a centroid, right? Now, I will say that whichever data points are nearby to the centroid, I am saying that all the unlabeled data has the same, label. So that is a strategy. Okay. Then distance-based nearest label point, which means unlabeled point is assigned the label of the nearest labeled sample within cluster. That is another one. So unlabeled point is assigned the label of the nearest labeled sample within the cluster. That means here we have to determine what is near, right? So that is where we use the feature space distance, that is distance between two data points depending on what features they have got, and using the distance which are closest, we can also use the same labels for the unlabeled data. Then there is also probabilistic or soft assignment, where unlabeled points receive labels based on the probability distribution of label samples in the cluster. Then another technique is there, which is unsupervised pre-processing and encoder-based SSL. Again, this you can revisit when you have done the lectures of the next module. Here we use the concept of, that means we try to find some, compact using pre-processing and using encoders, we actually can transform the data into, using PCA, principal component analysis, or using certain techniques where the dimensions of the data could be reduced further. Or rather, sometimes what we do is we understand the nature of those dimensions, and using that we can also try to find similar data points, and that actually help us in putting labels to unlabeled data. So raw input data is transformed into a compact latent representation, which is given by z equal to f theta of function of x, using techniques like PCA, autoencoder, scaling, and manifold learning before applying semi-supervised learning. So first we reduce the number of dimensions, or we rather find the meaningful dimensions which affects the nature of the data, and using those features we can do better predictions, right? We can so this actually improves feature quality, similarity structure, and robustness, leading to more accurate level propagation and better learning from limited labeled and unlabeled data. So because you are now looking into only the important features, that means it is better to determine similarity. We already learned what is similarity, the nature of the similarity, and all these things could be more, more robust measures, and that actually help us in better, finding the levels for the unlabeled data. Then there is active learning with semi-supervised learning with human in the loop. What is done here is it's basically a hybrid approach where the model learns from both unlabeled data and a human expert who labels the most informative or uncertain steps. So this is where we bring in people, and that means the labels based, looking at the data, the people is the one who is actually doing the prediction. So and this is done for the uncertain data. For the ones where the algorithm is more or less sure that yes, this is the level, then it's fine. For the points which are where the algorithm is not sure, the confidence level is not high, then I can bring in a human who would help me in classifying that, right? So difficult or high uncertainty points are selected for human annotation, while SSL propagates levels across the remaining unlabeled datasets. So what the selection function again could be depending on what basis should I select, which one should I give to a human to annotate, right? So there we use this function where unlabeled sample x star that is actually, we use the argmax selection score function over here. What it means is the highest selection, the one value with the highest selection score is chosen, right? So that means it is chosen for the level, of course. So there are different ways we can do that. So there is something called uncertainty sampling. Select samples where the model is most unsure, and that is this low confidence prediction is there. So that could be the way to select that particular sample, which I will determine which has to be given to a human encoder. Then margin sampling, select points closest to the decision boundary where we are not sure which side they will fall. Then entropy based selection, that is choose samples with highest prediction entropy, where we have already learned what is entropy earlier during decision trees. Then diversity sampling, where select samples that best represent different regions of the data, also could be brought in. So that means we would be doing annotation using those samples. So this selection function is actually selection function for the values which would need to get annotated by a human being. So this is the old data set that we are using. What we have done is, this data set, if you remember, the final decision is drive or bicycle, which is yes, no, that is given. And there are around 42 data points. And the day, the weather, the temperature, humidity, all these things are given. So and the wind levels, that is given. Now, based on that, I may make a decision to drive or not. So how do I find that, right? So in this case, earlier what we did was the entire data set was leveled and we ran a logistic regression or some other regression model to find the chances of which one would be the final label, right? Final outcome. But for a particular data point, right? That what is the result. But now what we have over here is some part of the data is labeled and this part of the data is not labeled at all. So this -1 indicates it is not labeled. So now we bring in the algorithms, we test the different algorithms that we have learned just now. So the first algorithm that we test is, of course, the label propagation. This is one of the most common ones, right? So the first part of the program is pretty standard. Import pandas from PD, import numpy as NP. From sklearn, we are importing column transformer, one-hot encoder, and then the semi-supervised import label propagation. This one we are bringing in. And then we are loading the data set first to DF. And then what we are taking is we are taking the columns from DF and storing it in X. So this is the ones which would be used for the model. And Y is basically the decision to drive bicycle or not. And it is mapped from 0, from yes becomes mapped to 1, no becomes mapped to 0. And if there are empty values or it is getting converted into integer and so on. So then the pre-processing step is, of course, the column transformer actually transforms, all the categorical to numeric values. So that is what is being done over here. And then what we are doing is we are the model has to be run, of course. So in the model, the label propagation model takes in the kernel value, which could be DBF, or in this case we have used KNN because we tried DBF, but DBF was not performing that good in this model, so we replaced it with KNN. And then total neighbor is given at 7, which basically means that within a distance of 7 neighbors, we will look for this propagation will happen. And total iteration is fixed as 200, so that is the maximum level of iteration that we can do. So then we do the model fit where X_ENC, that is, after pre-processing of the data that we have put over here, it becomes XCNC. Now it is, put inside the model. And once the model is fitted to that, and unlabeled mask is given as Y equal to -1, and then we can do the prediction of the unlabeled. And that is what is being done over here. Model.predict X_ENC unlabeled mask. So only for the unlabeled data, those would be predicted, right? And once we do that, we can store the data, and we can where prediction _unlabeled equal to 1, either yes or no, we can where this value is 1, then we print yes. That is that means then only we can go for printing yes or no, right? So based on whatever is being printed, so whatever is the prediction. So once we have done that, then we can print this data, and you can see that the result is being printed over here. So D18 to 2042 were unlabeled, and we are now having labels for this particular each of these predictions. Same exact way we do for label spreading. And the only difference being the first part and the last part is more or less same. The only difference being the model, which is the label spreading model instead of label propagation. And here also we are introducing the alpha factor 0.2. If you remember from the last slide or a couple of slides back, that alpha basically determines how close that means how much we should retain of the the labeled data, and how much we are allowing the the influence of neighbors and so on, right? So this neighbor is this again the iteration remains 200, And if you get the value set over for alpha is very low over here, it's 0.2. It says stay close to original level data, whereas high alpha means more influence of neighbors is taken, right? And 200 iteration is the maximum number of level propagation iterations. So this level spreading, actually, as we have said, it is that clamping thing is done. So that is happening over here. And then we using that, we can determine how much of clamping we need to do. And accordingly, we can set this figure. And once we do that, then again, we train the model, we predict the unlabeled data over here, and then we run the model and we get the results. And once we do that, then we can print it, and this is the result that we get, that all the unlabeled ones now gets predicted. Then finally we come to the self-training classifier. Again, remaining things remain, the other code remains same. We are now using, in this one, we are using the self-training classifier, and we are storing the data in here in this data frame. Then X values and Y values are being stored, and then we do the pre-processing using 1-hot encoder. And then once we have done that, then we the pre-processed data is transformed, and then from now we determine that, okay, logistic regression would be the base classifier, right? So so within the wrapper, this this would be logistic regression will become the base classifier, and 5000 is the number of iterations it will do, so that there is eventually convergence, to ensure there is convergence, or even though there is no convergence, the value would be more or less accurate. So the model, again, we are running with estimated equal to base, which is logistic regression. Threshold is 0.7, which means that the confidence, that means the base classifier plus pseudo labeling, the threshold is 0.7 is the confidence cutoff for accepting pseudo label. So this we already discussed earlier, that is, we use the confidence level of the data. That means we can calculate the confidence level. If it is above 0.7, then only we will accept it, otherwise not, right? So that is what is being given over here, and the criteria is given as threshold, and this extract features vectors and assigns final predicted levels after self-training, right? So once the model is run, we can fit, of course, we are fitting the model here, and then again unlabeled mask, and then we are predicting the unlabeled, and for the where the data is already masked with unlabeled mask, for those ones we are predicting. So again, this part remains same, that is, we are storing the different variables which we are putting there, and then this transduction is a special attribute that we are doing over here. What it does is, it is a special attribute of self-training classifier which stores the final levels assigned to all training samples using the pseudo levels as well. That means it tells us that which one are pseudo levels and which one are the actual levels, right? And this accepted actually is basically that we are counting the number of pseudo levels, that means that are there, right? So this it is stored in accepted, and it counts how many unlabeled samples received confident pseudo levels, right? So that means out of the ones predicted which were having above pseudo confidence level of whatever we have said, this is the disband for that. And so once we run this program, so it is basically we are running the semi-supervised program where we are determining what would be the base classifier, and the rest of the process is pretty standard. It using the base classifier method and the confidence interval, the confidence level, not interval. We can determine which predictions to keep, which not to keep, and we keep on iterating when everything is properly predicted and also within confidence level. So this is the final results that we got, and if you compare, you see there are some differences between the output of the three algorithms. So these are some of the references you can study. And to conclude, semi-supervised learning is particularly valuable in urban analytics where labeled survey data is scarce, but large volumes of unlabeled spatial mobility and IoT data are available. Thank you.